Use the Maclaurin series expansion for e to the x to write down power series expansions for e to the 2x, e to the 4x, and e to the nx, where n is some positive integer. So one thing I should say, I tend to write things in terms of n's when I'm defining series using series notation. Because I've got this e to the nx, I'm going to use k's instead. I'm just going to make a little note there because I have a habit of using n's and not k's. If I have an n going on and then I'm looking at the sum of terms from n equals something to something out to infinity, that's not going to work. So I'm going to need to use k's for my series notation or sigma notation. Part B. Use the Maclaurin series expansion for cosine x to find the first two non-zero terms of the Maclaurin series expansion of cosine e to the x. And then, actually, it probably should say hence there, because part B definitely uses the results from part A. Part C does say hence show that for x near 0, cosine of e to the x is approximately equal to cosine 1 minus sine 1x, so we can't possibly understand that without having done A and B. And then find by direct calculation the Maclaurin polynomial of degree 2 of cosine e to the x. So often the actual calculation part is easy, but I'm not sure, having not actually done the question yet. So again, this is from your formula book. We're going to use actual standard Maclaurin expansion. So we're not going to start with f0, f-0, f-0. We're just going to use what we've got in our formula book. So e to the x is just given right here, and we're just going to do it like that. We're going to need e to the 2x, e to the 4x, and e to the nx for some positive integer n. So if we start with our e, it all goes from e to the x. So as you can see from the formula book, e to the x equals, well, it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... And if you just look at what's going on, powers are going up by 1 each time. So we start with x to the power 0, x to the power 1, x to the power 2, and so on. And think in terms of the factorial, this could be 0 factorial, 1 factorial, 2 factorial. Now, I was just about to put x to the n over n factorial, but I just need to remind myself I need to work in k's for this question. Otherwise, I'm going to have awful trouble when I get to that n bit. So I'm going to say plus x to the k over k factorial, right? So that's our e to the x, which could be defined in series form. So e to the x equals the sum from k equals 0 to infinity of x to the k over k factorial. Right, so just get the labeling on the questions right. We've got part 1, part 2, and part 3. So for part 1, e to the 2x, well, all we're going to do is write out the same series, use the e to the x Maclaurin series, but we're just going to replace x with 2x. So it's going to be 1 plus 2x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial plus ... plus, well, it's going to be 2x to the power k over k factorial. So you could just leave it like that, or I suppose for the first few terms you could say, well, e to the 2x equals 1 plus 2x plus, well, 2x squared is 4x squared, so 4x squared over 2 factorial plus 2 cubed is 8, so 8x cubed over 3 factorial plus ... And I suppose if we're doing it like that, well, it's going to be 2 to the k, x to the k over k factorial. So e to the 2x is going to be the sum from k equals 0 to infinity of 2 to the k x to the k over k factorial. Okay, part 2, we need to find e to the 4x. Very, very similar. So e to the 4x is going to be 1 plus 4x plus, I might just do it in this, but it's going to be 4x squared. 4x squared over 2 factorial plus 4x cubed over 3 factorial plus dot 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 plus 4x to the k over k factorial. Might just expand that a little bit, potentially not necessary, but I'll do it anyway. So you could say e to the 4x equals 1 plus 4x plus 16x squared over 2 factorial plus 4 cubed is 64, 64x cubed over 3 factorial plus dot 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 plus 4 to the k x to the k over k factorial. So I should have left myself a little bit more room. See if I can squeeze it in. So e to the 4x equals the sum from k equals 0 to infinity of 4 to the k x to the k over k factorial. The third part was asking for, that was part 2, the third part was asking for e to the nx. E to the nx, well, I'm going to go straight into this form now, so it's 1 plus nx plus, well, it's going to be n squared x squared over 2 factorial plus n cubed x cubed over 3 factorial plus dot 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 plus, well, it's going to be n to the k x to the k over k factorial. So that would mean e to the nx equals the sum from k equals 0 to infinity of n to the k x to the k over k factorial. So now for that particular example, you can see why we really need the k's. And that was part 3. Okay, so just so we're clear and I can reference things without having to go all the way up the page, just move these two things on screen. Use the Maclaurin series expansion of cosine x to find the first non-zero terms of the Maclaurin series expansion of cosine e to the x. So don't let this, something like this, first 2 non-zero terms, you don't need to think about that yet. Let's do the expansion and then we'll think about whether terms are 0 or non-zero later. But basically, we need to do this first, Maclaurin series expansion of cosine x, and then we need to turn it into that. We will go from there. Okay, so if we first write down the series for cosine x. So cos x equals, well, it's 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus dot dot dot. If we look at the powers of x are 0, 2, 4, 6. So if n started at 0, it's x to the power 2n. So we've definitely got an x to the power 2n in there. We've got an alternating series thing going on in signs. So if we start with n being 0, if we had minus 1 to the power n, minus 1 to the power of 0 will give us a positive first term. So we can say minus 1 to the power n, x to the 2n over, and then the factorial is exactly the same as the power. So that is 2n factorial, right? So that's our cosine x. Now, do keep in mind, now we can apply this to find cosine e to the x. So cos e to the x. And remember, we're just trying to get an idea for what's going on. And then we're hoping that the next step for finding these first 2 non-zero terms will become apparent. So it's going to be 1 minus x squared, so that would be e to the x, squared over 2 factorial plus x to the 4 over 4 factorial. That would be e to the x to the 4 over 4 factorial. Going to skip the 6. I'm just going to say plus dot 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 plus minus 1 to the n, and then e to the x to the 2n over 2n factorial. And then let's just think about what that means in terms of just basic index laws. What is e to the x squared? What is e to the x to the power 4? So that looks like this. 1 minus, well, e to the x squared is e to the 2x over 2 factorial plus e to the 4x over 4 factorial plus dot 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 plus then we've got minus 1 to the n. This is going to get a little bit complicated. It's going to be e to the 2nx, e to the 2nx over 2n factorial, right? So that's going to get a bit messy, but we don't have to go far with it. We just need a couple of terms. So now we can go to write this out. So this is going to be 1 minus, now for this e to the 2x over 2 factorial, I'm going to pull the 1 over 2 factorial out, so the minus 1 over 2 factorial. And then I'm going to put just a little bit of the power series for e to the 2x. The e to the 2x was this. It was 1 plus 2x plus 4x squared over 2 factorial and so on. So 1 plus 2x plus 4x squared over 2 factorial plus dot dot dot. I'm not going to go any further than that because now I'm getting an idea, because I'm only interested in the first two non-zero terms, which are going to be just, assuming that they're both non-zero, it's just going to be the constant, as in the term without the x's, and the x's. Anything bigger than that, x squared, x to the 4, x to the 5, and so on, it's not going to be part of it. So now, the next term, just in the same way, we're going to pull out that 1 over 4 factorial, and then we're going to have the power series for e to the 4x, which was 1 plus 4x, plus, remember, it was 4x squared over 2 factorial, so that was 16x squared over 2 factorial plus dot dot dot. And that just continues. So now the final term is going to be plus dot 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 plus, and you're going to have minus 1 to the n over 2n factorial. And then we've got what is power series for e to the 2nx. Well, we know what the power series for nx looks like. It goes 1 plus nx plus n squared x squared over 2 factorial. So for 2nx, well, I only have to go up to x, it's going to be 1 plus 2nx. And then I suppose we could put the next, I don't even really care about the next term, to be honest, but it would be 2n squared x squared, the whole 2n's being squared over 2 factorial. And I don't even care about expanding that, it's not a problem. So now we can think about these first two non-zero terms. So remember, the first two non-zero terms of the expansion. So that is going to be some constant term plus something to do with x. So get the highlighter. Look at the way the constant terms are generated. Well, firstly, you've got this 1, and then you've got a minus 1 over 2 factorial times a 1. And then nothing else in that first bracket will contribute a constant term. It's all got powers of x in. So then we go to the next bracket, and you have this 1 over 4 factorial times 1 contributes to the constant term. It's a number with no x's. And then we go all the way to the end, and you've got this, so minus 1 to the n over 2n factorial times 1. So that is going to give us our constant term, and it's definitely non-zero. So if we then take a similar approach for the second non-zero term, which would be an x, well, look, you're going to have 2x times minus 1 over 2 factorial. Everything else in that bracket is going to be bigger powers of x. Not interested. Go to the second bracket. You've got 4x times 1 over 4 factorial. Go to the last bracket. You've got 2nx times 1 over 2n factorial. So we're going to have 1 minus 1 over 2 factorial plus 1 over 4 factorial minus 1 over 6 factorial and so on, all the way up to the last term plus minus 1 to the n over 2n factorial. Remember, all of these will just be multiplied by 1, so this is a constant term, clearly non-zero, and then plus, well, we've got our x term, so I'm just going to pull an x out there, and then we're going to think, well, everything that had x is in, so we start at the top. It was, well, it's minus 1 over 2 factorial times 2. We've already pulled the x out, so think about that. You've got 2 over 2 factorial, well, that really, it's 2 over 2 times 1 factorial. And I'm going to write this as 1 over 1 factorial. You will see the reason for that very soon. So plus x times minus 1 over 1 factorial. But obviously, yes, that is just 1. But I want to define it using a sigma notation very soon. Next term is positive, comes from that second bracket, and it is 1 over 4 factorial times 4. So you remember, it's 4 over 4 factorial can be written as 4 times 3 factorial. So that becomes 1 over 3 factorial. And now we can see a pattern, 1 over 1 factorial, 1 over 3 factorial, plus 1 over 3 factorial. So then the next one, deducing, it's going to be minus 1 over 5 factorial for exactly the same reason, plus dot, dot, dot. In fact, I'm not going to fit that, so I'm going to remove that next term, but we saw what it was anyway. So plus, dot, 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 plus, and then we're on this last term, which is, so it's minus 1 to the n, and then it is 2, we've already pulled the x out, so it's 2n over 2n factorial. Just think, 2n, do it in a different colour, so 2n factorial in the same way could be written as 2n times 2n minus 1 factorial, exactly the same principle. So this last one is going to be 1 over 2n minus 1 factorial. So I'm just going to write that as minus 1 to the power n over 2n minus 1 factorial, and that is our x term. So if we tidy all of this out, now you've got a choice. You can either, for this constant term, you could leave the 1 out and then define a series starting from 1, or you could leave the 1 in and define it starting from 0. Then we can go with think of the factorials and the powers of n. Just think of the factorials, they're going up in 2s. So I'm going to say this is 1, and that's this 1 here, plus the sum from n equals 1 to infinity. I'm just trying to define the constant term. So that's all of these factorials times, then now I want to start with a negative first term. So it's still going to be minus 1 to the n over 2n factorial. I'm going to have minus 1 to the n over 2n factorial. So that's the constant bit, plus I'll put the x in near the sigma bit. So now I want to define this sequence here for the x part, which is going to be the sum from n equals 1 to infinity, and it's going to be minus 1 to the power n over 2n minus 1 factorial, and don't forget the x. Okay, so that's quite an important result, so I'm just going to box that. That is the first two non-zero terms of the Maclaurin series for cosine of e to the x, and that was the end of part B. And show that for x near 0, cosine e to the x is approximately equal to cosine 1 minus sine 1 of x. So the argument for this is to say that as x approaches 0, so basically x squared really approaches 0, x cubed is getting even closer to 0. So the argument, basically, we disregard higher powers. So higher powers of x are very close to 0. And that's why, and that means cosine of e to the x is going to be approximately equal, it's going to be very close for very low x's, approximately equal to the series that we just worked out, which is the 1 plus the sum from n equals 1 to infinity of minus 1 to the n over 2n factorial plus the x bit, the sum from n equals 1 to infinity of minus 1 to the n x over 2n minus 1 factorial. So we're saying that for very low x's, this approximation will be very good. Now for the next bit, we're actually going to use the Maclaurin series of cosine x and sine x, so that's why I put them up here, just for good reference. So cos 1 equals, going straight from the series, 1 minus 1 squared over 2 factorial plus 1 to the 4 over 4 factorial. So 1 squared over 2 factorial is 1 over 2 factorial plus 1 to the 4 over 4 factorial plus dot, dot, dot. Try and define this using series notation. Now I'm going to ignore the 1. I'm going to hope that this 1 here can be equivalent to that 1. I'm trying to show that these things are equal. So we're going to say that equals 1 plus the sum from n equals 1 to infinity. Now remember, I'm only considering the factorial bit. There's a power in there. The first one's negative, so it must be minus 1 to the n. Over, and then it's 2n factorial, because it's 2 factorial, 4 factorial, 6 factorial. So already, you remember what we're trying to show? Show that cosine e to the x approximately equals cosine 1 minus sine 1 times x. Well, the cosine 1 bit, we've already got this and this, which you should notice is exactly equivalent to this and this. So we're just, as long as the sign matches up with the rest, then it's fine. So using exactly the same line of reasoning, sine 1 equals, just go straight to its Maclaurin series, 1 minus 1 cubed over 3 factorial. So that's 1 over 3 factorial plus 1 to the 5, which is 1 over 5 factorial plus dot, dot, dot. Just being careful with the negative sign, we have been asked to show that this is cosine 1 minus sine 1x. So let's work out the expression for minus sine 1. So minus sine 1 is going to be exactly that, so minus 1, but the sign's changed obviously. Plus 1 over 3 factorial minus 1 over 5 factorial. So that could be written as the sum from n equals 1 to infinity of, so the first term's negative, so that's minus 1 to the n. And on the bottom, you've got 1 factorial, 3 factorial, 5 factorial. So we've got our 2n minus 1 factorial. So we're nearly there. It's just we need to show that it is the same as minus sine 1x. So if we just times that by x, minus sine 1x, well that is just going to be all of that, but with an x, equals the sum from n equals 1 to infinity of minus 1 to the n over 2n minus 1 factorial x. So if we put that together, just to show you, so this here is supposed to be exactly equivalent to our minus sine 1x. So that's the sum from n equals 1 to infinity minus 1 to the n x over 2n minus 1 factorial. The sum from n equals 1 to infinity minus 1 to the n x over 2n minus 1 factorial. So that shows us that for x close to 0, cosine of e to the x is approximately equal to, it was cos 1 minus sine of 1 times x as required. Okay, so part D, find by direct calculation the Maclaurin polynomial of degree 2 of cosine e to the x. So actually, for the first time in the whole question, we're going to have to begin with the Maclaurin series. So we're going to need f of x equals cos e to the x. So f of 0 is going to be what's cos e to the 0, which is cos 1, which we'll leave like that. So f dashed x is going to be, well, it's minus sine of e to the x times the derivative of the bit in the bracket. E to the x differentiates to itself, so times e to the x. F dashed 0 is going to be, well, e to the 0 is 1, so it's minus sine of 1 times 1, so that's minus sine 1. Just think, we've got a cos 1 and a minus sine 1. We've used both of those previously. And then we're going to need, just think of how the Maclaurin series goes, it's going to be f0 plus f dashed 0 times x plus f dashed 0 times x squared over 2 factorial. So we're going to need one more. F dashed x is not so simple because we have a product, unfortunately. So you've got a u and a v. So it's v du by dx times u dv by dx. So it's going to be, if we say that the sine e to the x can be u, so if we say that u equals our minus sine e to the x, well, then our u dashed is going to be, well, minus sine differential to minus cos, so minus cos of e to the x times e to the x. If we let v be the e to the x here, and then v dashed is just going to be e to the x again. So f dashed x is going to be u dv by dx plus v du by dx. So u times dv by dx, it's going to be u, so minus sine e to the x times dv by dx, which is e to the x, so will it be minus e to the x sine e to the x. So that is u dv by dx, and we need a v du by dx, which is going to be e to the x times e to the x times minus cos e to the x. So e to the x times e to the x is e to the x squared, which is e to the 2x. It's negative, so minus e to the 2x times cos e to the x. Okay, so now we need f dashed 0. Well, it's going to be minus e to the 0, which is minus 1, times sine e to the 0, which is sine 1. So it's minus sine 1, and then we've got another minus, and then you've got e to the 2 times 0, so e to the 0, which is 1. And then you've got cosine e to the 0, which is cosine 1, so minus cos 1. So now we have our f dash dash 0, we have our f of 0, and we have our f dashed 0. So now we can put those in. So now our Maclaurin polynomial of degree 2 equals, so we're going to just say f of x, which remember is our Taylor polynomial of degree 2 centered at 0, is, well, it's f of 0 cosine 1 plus f dashed 0, so that's minus sine 1x, and then the final bit plus f dashed 0, so that's all of this, which is negative, so I'm going to pull that out, minus sine 1 plus cos 1 times x squared over 2 factorial. And it doesn't want us to go any further than that. So that question was a bit of a marathon, to say the least, but we have gotten to the end of it, and I think you get exam questions. There will, obviously, the exam is quite short compared to what you get in a book, but the skills will be there, but I don't think they're going to give you anything quite as hefty.